welcome back to our AS Level Further Mathematics Past Paper Walkthrough series. I'm Hayat and I will be your video host for today's session. Today we'll have Siddharth as our contributor who will explain to you all the things that you need to know while doing the paper Winter 2023 and Paper 12. So are you ready? Let's get started.
So use standard results from the list of formulae to find the summation of 3r squared plus 3r plus 1 in terms of n and simplify your answer. So this is an easy one. So this will just be 3 sum of r squared plus 3 sum of r plus the summation of 1. All from 1 to n, but I want to write that since it's just gonna take up space. So this will be 3 by 6 into n plus 1 into 2n plus 1 plus 3 into n plus 1 by 2 plus n. So this is just going to be n into n plus 1 plus into 2n plus 1 by 2 plus 3n into n plus 1 by 2. We can write this as 2n plus 2n by 2. And factoring out the n by 2, we get n by 2 into n plus 1 into 2n plus 1 plus 3n into n plus 1 plus 2. So we can simplify and we'll get n by 2 into 2n squared plus 3n plus 1 plus 3n squared plus 3n plus 2. And this just becomes n by 2 into 2n squared. This is 3. Yeah. Sorry for that. It's 2n squared plus 3n plus 1 into 3n plus 3 plus 2. So it becomes 2n squared plus 6n plus 6. Yeah. So this just becomes n. We distribute the brackets. We get n cubed plus 3n plus 3. 3n squared plus 3. Yeah. Show that 1 by r cube minus 1 by r plus 1 whole cube is equal to 3r squared plus 3r plus 1 by r cube plus r cube into r plus 1 whole cube. And use the method of differences to find out this sum. So let's do that. So 1 by r cube minus 1 by r plus 1 cube. So just take the LCM. We get r plus 1 cube minus r cube divided by r cube into r plus 1 cube. So this becomes r cube plus 3r squared plus 3r plus 1 minus r cube, all divided by r cube into r plus 1 cube. So here we have 3r squared plus 3r plus 1 divided by r cube into r plus 1 whole cube. So we have shown. So I'll erase this now, but you'll have to keep it in the exam. So now that we've shown this, let's calculate this sum. So this can just be written as the sum from r is equal to 1 to n of 1 by r cube minus 1 by r plus 1 whole cube, right? So substituting r is equal to 1, we get 1 by 1 cube minus 1 by 2 cube, and then add 1 by 2 cube minus 1 by 3 cube plus 1 by 3 cube minus 1 by 4 cube, all the way on and on until we reach n. So we get 1 by n cube minus 1 by n plus 1 whole cube. So what we note is this plus 2 cube and this minus 2 cube cancel. 1 by 2 cube actually. 1 by 3 cube and minus 1 by 3 cube cancel, and on until we are left with just 1 by 1 cube minus 1 by n plus 1 cube. It's just 1 minus 1 by n plus 1 cube. So this is our final answer. Okay, so deduce the value of the sum from 1 to infinity of the sum. So we previously got that the sum from 1 to n was just 1 minus 1 by n plus 1 whole cube. So here it's nothing, it's almost the same thing except n is just infinity. So if we take the limit as n tends towards infinity, this denominator gets much bigger, and 1 divided by a very big number just tends towards 0. So it becomes 1 minus 0, which is just 1. Let's move to the next question. Prove by mathematical induction that for all positive integers n, dn by dx to the power n of x squared e to the x is just this x squared plus 2nx plus n into n minus 1 times e to the x. So the format for proof by induction is always the same. It's just check the base case first, where n is equal to 1. So they've said that all positive integers. So the first positive integer is 1. So let's check that now. So d by dx of x square e to the x. So according to the formula, what we're going to get is x square plus 2x plus 1 into 1 minus 0 is just 0. So we'll just leave that e to the x. So this, as per the formula, we can call this the left-hand side. Now let's manually differentiate this. Using the product rule, we get 2x e to the x plus x square e to the x. Factoring out the e to the x, we get e to the x times 2x plus x square, which is the same thing. So it's the RHS. So since LHS is equal to RHS, the formula is true for n is equal to 1. Okay, let's move to the next part, which now we have to assume that for n is equal to k, dk by dx to the power k of x square e to the x is equal to x square plus 2kx plus k into k minus 1 times e to the x. So this is what we have to assume as true. Now let's check for, you don't have to write the let's in example. Just check for n is equal to k plus 1. And then we get dk plus 1 by dxk plus 1 of x square e to the x. So this is nothing but d by dx of dk by dxk of e to the x. And we already assumed that this was equal to x square plus 2kx, so on, x square plus 2kx plus kx k into k minus 1 times e to the x, didn't we? So let's differentiate this now. So again, we can just use the product rule. This is the first function, this is the second function. So differentiating the first side, then we get 2x plus 2k, that's just a constant, we can leave it, into e to the x plus x square plus 2kx plus k into k minus 1 e to the x. Now we can factor out the e to the x again. Let's leave it here. And what do we get? We get x square plus 2kx plus 2x is just 2 into k plus 1x, and k into k minus 1 plus 2k. Sorry, 1 second. So I'll write it more neatly here. So we have x square plus 2kx plus 2x plus k into k minus 1 plus 2k. So this is what we have to factorize on the left hand side. So we have x squared plus 2k is 1x plus what we do? Yeah, plus this is going to be k into k minus 1 plus 2. So this becomes x squared plus 2 into k plus 1x plus k into k plus 1. Yeah. So this is what we get by manually differentiating it. I'll erase this statement at the top and I'll write that down here. So of x square plus 2 into k plus 1 x plus k into k plus 1 times e to the x. So now note that this is what we get if we directly plug k plus 1 into the formula itself. So using the formula given, so we get x square plus substituting k plus 1 for n, we get k plus 1x plus substituting k plus 1 again, we have k plus 1 into k plus 1 into k minus into k plus 1 minus 1 is just k. So this is what we get, e to the k, e to the x. So this is the same thing as this. So LHS is equal to RHS. So formula holds true for n is equal to k plus 1. So now we have to write the final concluding statement. Since formula holds true for n is equal to 1, k and k plus 1, it holds true for all positive integers. So that's all for this question. So the matrix M is given by M is equal to this matrix times this matrix. So where k is a constant and it's not equal to 0 or 1. Okay. So the matrix M represents a sequence of two geometrical transformations. State the type of each transformation and make clear the order in which they are applied. So in matrices, the transformations are always applied right to left. So we check this one first. What the first column of this matrix means is that in the xy plane, the I hat vector, the unit vector 1, 0 is going to 1, 1. So it looks like this. So it went from 1, 0 to 1, 1. And this column represents the j hat vector 0, 1, and it stays as it is. So what this first matrix represents is a shear keeping the y-axis fixed. Okay, so by 1 unit, if you want to be specific. And the second matrix is a stretch. So what this means is that the first, the unit vector 1, 0 is getting stretched all the way to k0, while the unit vector in the y direction j hat stays as it is. So this is a stretch parallel to x-axis by scale factor k. Yep. So the unit square in the xy plane is transformed by m onto the parallelogram OPQR. Find in terms of k the area of parallelogram OPQR and the matrix which transforms it back onto the unit square. So the area of this is by definition the determinant of matrix M. So let's find out what that is. So it's k0, 0, 1 into 1, 1, 0, 1. So let's make this a single matrix. Let's do the matrix multiplication. So it's going to be k into 1 plus 0, k into 1 plus 0 into 1, which is just k. And then we got k into 0 plus 0 into 1, which is 0. Second. Okay. And then we got 1 into 0 plus 1 into 1, which is 1. And 1 again here. Yeah. Okay. So the determinant of this is going to be AD minus BC. So k into 1 minus 0 into 1, which is just k. So the determinant of m is going to be k. So the area of this parallelogram is going to be k, absolute value of k actually, technically speaking. Okay, so find the matrix which transforms OPQR back onto the unit square. So this is going to be the inverse matrix. So the inverse matrix is going to be, if you have a matrix like A, B, C, D, the inverse matrix is going to be 1 by AD minus BC into DA minus B minus C. So since we had, what was it? I think so it's K011. Yeah. So this is going to be the inverse of this. So M inverse is going to be 1 by K, the determinant, into 1 K and minus 0 minus 1. So minus 0 is just 0. So, yep. So that's the inverse matrix. And the determinant, the area of the parallelogram, is going to be absolute value of K. So show that so we're on the next part. Show that the line through the origin with gradient 1 by k minus 1 is invariant under the transformation in the xy plane represented by m. Okay, so for a line to be invariant means that basically all the points on the line stay on the line even after the transformation is applied. So we've got the matrix M, which is just K011. Okay, so if we multiply it by point x mx, we get another point on the same line, capital X and capital MX. So this should be satisfied for the line to be invariant. So let's check it when the gradient is equal to 1 by k minus 1. So we've got m is equal to 1 by k minus 1. So k011 into x into x by k minus 1. So this becomes a vector. So we get kx, and it is a k into x plus 0 into k by k minus 1. And on the second row, we get x plus x by k minus 1. So we can write this as kx by x into k minus 1 plus x by k minus 1. And this becomes kx into k minus 1 plus x is nothing but kx minus x plus x. So this becomes kx by x minus 1. So this actually satisfies our initial condition, since we can write this as nothing but kx and kx into 1 by k minus 1. Remember that 1 by k minus 1 is nothing but our m. If we compare this with the original, we have x here, which is kx, and we have x here again, kx, and m, which is 1 by k minus 1. So it's been shown. So let's move to the next question. The cubic equation 27x cubed plus 18x squared plus 6x minus 1 has roots alpha, beta, gamma. Show that a cubic equation with roots 3 alpha plus 1 plus 3 beta plus 1 plus 3 and not plus 3 gamma plus 1 is this one. Okay, so let's do this. We got 27x cubed plus 18x squared plus 6x minus 1 is equal to 0. So let's say y is equal to 3x plus 1. So comparing with this one, with these roots. So y minus 1 by 3 can be said to be equal to x, right? So let's substitute this over here for all the x's. Okay. So we get 27 into y minus 1 cube by 3 cube plus 18 into y minus 1 squared by 3 squared. Just give me a second. plus 6 into y minus 1 by 3 minus 1 is equal to 0. So 27 by 3 cube is just 1. So we get y minus 1 cube plus 18 by 9 is just 2 into y minus 1 squared plus 2 into y minus 1 minus 1 is equal to 0. So this becomes y cube minus 3y square plus 3y minus 1 plus 2 into y minus 1 square is just y squared minus 2y plus 1. And let's distribute that out. So we get 2y square minus 4y plus 2 plus 2y minus 2 minus 1 is equal to 0. So we got this leads us to y cube. Okay, so minus 3y square plus 2y square is just minus y square. 3y minus 4y plus 2y, that's going to be 5. Okay, yeah, plus y. And minus 1 plus 2 minus 2 minus 1 is just going to be minus 2 is equal to 0. So this is what we have. So it's been shown. So let's move to the next question. The sum 3 alpha plus 1 to the power n plus 3 beta plus 1 to the power n plus 3 gamma plus 1 to the power n is denoted by s sub n. So find the values of s2 and s3. So this means basically the sum of squares. So 3 alpha plus 1 square plus 3 beta plus 1 square. Okay. So there's a very simple identity. You need to know this. It's for example, if you have a square plus b square plus c square, you can just write it as a plus b plus c whole square minus 2 into ab plus ac plus bc, like this. So this 3 alpha plus 1 whole square plus 3 beta plus 1 whole square plus 3 gamma plus 1 whole square, we can just write this as the sum of roots 3 alpha plus 1 plus 3 beta plus 1 plus 3 gamma plus 1 whole square minus 2 into the multiples of the roots. So what you notice is this is nothing but sum of roots whole squared minus 2 times the sum of roots taken 2 at a time. Right? So this is going to be minus b by a whole square minus 2 into c by a. So this 3 alpha plus 1 and all are the roots of this equation. Y cube minus y square plus y minus 2 is equal to 0, right? So what's b and a here? So b is going to be minus 1 and a is 1. So minus of minus 1 by 1 is just 1 square. Minus 2 into c by a. C is also 1. So 1 by 1. So it's just going to be minus 1. Right? So S2 is equal to minus 1. Let's remove that here. So let's find out what S3 is. So let's write down the equation again. So we got y cube minus y square plus y minus 2 is equal to 0. Is that it? Cube, yeah. So since I'll denote this A, capital A, B, C, right? So since these are all roots, they satisfy this equation. So we can write a cube minus a square plus a minus 2 is equal to 0. And b cube minus b square plus b minus 2 is equal to 0. And c cube minus c square plus c minus 2 is equal to 0, right? So notice this. I'll just erase this. If we add up all the equations, we get a cube plus b cube plus c cube. We just add it all up. 1 second. And then we got minus a square plus b square plus c square plus a plus b plus c minus 6 is equal to 0. So this is what they're asking us to find out, which is the sum of the cubes. So and we already know this and this. So let's just call this, for example, x. So x minus, this is nothing but s2, which is just minus 1. X minus minus 1 plus a plus b plus c. This is the sum of roots, which is minus b by a, which is just 1. This 1 minus 6 is equal to 0. So x plus 1 plus 1 minus 6 is equal to 0. X is equal to 6 minus 2, 4. Okay, so S3 is equal to 4. Okay, let's move to the next one. Find the values of S minus 1 and S minus 2. So that's 1 by capital A plus 1 by capital B plus 1 by capital C. So taking the LCM, we get BC plus AC plus AB divided by ABC, right? Straight. Sorry if it's a bit slant, by the way. Better keep it straighter. So this is nothing but the roots taken two at a time, which is C by A, and this is the product of the roots, which is minus D by A. Right? This A cancels out, so we got C by minus D. So the equation was y cube minus y squared plus y minus 2 is equal to 0. So C by minus D is just going to be 1 by minus of minus 2 is 2. So it's 1 by 2. Okay. So S minus 1 is equal to 1 by 2. Let's find S of minus 2. Right, so S minus 1 is equal to 1 by 2. So S of minus 2, that's going to be a little more complicated, but we can still do it. So we got y cube minus y square plus y minus 2 is equal to 0. So if we divide the whole equation by y square, what do we get? We get y minus 1 plus 1 by y square. Oh, sorry, 1 by y. Minus 2 by y square is equal to 0. And similar to how we did with this question, if we just substitute a, b, c, and again add it all up, what do we get? So we're going to get like sum of the roots minus 3 plus sum of the one reciprocal roots minus 2 times sum of 1 by the reciprocal root squared. So we already know this, the sum of the roots, that's just 1. We already did it. So it's 1 minus 3 plus, this is a sum, and we just found this out, that was 1 by 2 plus 1 by 2 minus 2x is equal to 0. So let's just call this x. So 1 minus 3, 2 minus 2 plus 1 by 2, it's going to be minus 3 by 2 is equal to 2x. So x is going to be equal to minus 3 by 4. So s minus 2 is equal to minus 3 by 4. Okay, so that's this question solved. Okay, let's move to the next question. The plane pi1 has equation r is equal to 1 minus j. Okay, we'll write this in vector form. So 1 minus 1 minus 2 plus lambda of 1 minus 2 minus 3 plus mu 3 0 minus 1. There's no j here, so it's 0. Okay. So find the, basically they're asking us to find the Cartesian equation of the plane. So for the Cartesian equation, we just need to know two direction vectors on the plane and 1 point on the plane. So we already have two direction vectors. That's this one, 1 minus 2 minus 3 and 3 0 minus 1. So let's find the normal vector. So normal vector is equal to I j k into 1 minus 2 minus 3 and 3 0 minus 1. So we can do this will just be minus 2 into minus 1, which is minus 2 into minus 1 minus minus 3 into 0. So that's just 2. And then minus, remember for the j column we always put a minus. It's like a cofactor thing. So plus minus plus. So So 1 into minus 1 minus 3 into 3, which is 1 into minus 1 minus 3 into 3. Yeah. Minus 1 plus 9. That's going to be 8. Okay. And finally, we got k is 1 into 0 minus 2 into 3, which is going to be 6. Right? Not the brackets. So this is going to be 2 minus 8, 6. So that's the normal vector. So normal vector times xyz is equal to normal vector, it's a dot product, normal vector dot any point of the plane. So let's take any point of the plane, which is 1, minus 1, minus 2. Okay. So substitute this what we found for the normal vector. We got 2 minus 8, 6 into xyz is equal to 2 minus 8, 6 into 1 minus 1 minus 2. So this becomes 2x minus 8y plus 6z is equal to 2 into 1, which is 2, plus minus 8 into minus 1, which is plus 8, plus 6 into minus 2, which is minus 12. So 2 plus 8 minus 12, that's 10. That's going to be minus 2, right? So we got 2x minus 8y plus 6z is equal to minus 2. And we can divide the whole thing by minus 2 to get x minus 4y plus 3z is equal to minus 1. Yeah. So the line which does not lie in pi 1 has equation r is equal to minus 3 1 plus k plus t into ijk, I plus j plus k. Show that L is parallel to pi 1. Okay, so for it to be parallel, what does it mean? So, for example, this plane is there and it has a normal vector. Okay, so its normal vector is there. So there's this other line L, which is something like this. So parallel means it's going to be perpendicular to the normal vector, right? And if it's perpendicular, the direction vector of this line L with the times the dot product of this normal vector is going to be 0. So that's how we show that it's parallel. So that's the direction vector is this is ijk dot. The normal vector is what we can also take 1 minus 4 3 instead of 2 minus 8 6, since it's almost the same thing. So 1 minus 4 3. So this should be equal to 0 for it to be parallel. So let's calculate it. So 1 into 1 is just not ijk, by the way, 1 1 1. Take the coefficients. So 1 into 1 is going to be 1. 1 into minus 4 is minus 4. 1 into 3 is 3. So this is 1 minus 4 minus 3. Minus 3 plus 3 is 0. So it's 0. So it's got to be parallel. So that's it. That's it's shown. Find the distance between L and pi 1. Okay, since it's parallel, all the points will have the same direct perpendicular distance. So we can just take this point on the plane minus 3 plus k. So it's minus 3 k 1 0. It's minus 3 1 0. Okay. So this distance, so and the plane, what was the equation? X minus 4y plus 3z. X is equal to minus 1. Okay. So the formula for a distance from point to plane is going to be ax plus by plus cz minus t by square root of a square plus b square plus c square. So that's the distance. Actually, absolute one. Yeah. So let's take, so a is going to be this coefficient, that's going to be 1. So 1 into minus 3 plus minus 4 into 1 plus 3 into 0 is just going to be 0 minus minus t, so it's going to be plus 1 divided by square root of 1 square plus 4 square plus 3 square. So let's calculate this figure. Just give me a second, some calculation mistake. 1 second, what did I do here? Oh, it's minus 301, not minus 310. Okay. A lot of silly mistakes today. Okay. So it's going to be 1 into minus 3 minus 4 into 0 is going to be 0 plus 3 into 1 is going to be 3. So this is going to be minus 3 plus 3 is going to be 0. 0 plus 1 is 1. 1 by root this is 26. So that's the answer. That's the distance between L and pi 1. Okay, the plane pi 2 has equation 3x plus 3y plus 2z is equal to 1. So find a vector equation of the line of intersection of pi 1 and pi 2. So first let's find out a common intersection point. So we got 3x plus 3y plus 2z is equal to 1. And we also have x minus 4y plus 3z is equal to minus 1. X minus 4y plus 3z. That is a bad 3. Is equal to minus 1. Yeah. So here what we can do is just take, for example, any of the variables to be equal to 0 and take it into a simultaneous equation. So for example, let's take z as equal to 0. So we get 3x plus 3y is equal to 1 and x minus 4y is equal to minus 1. So solving this, I'm just going to solve this directly in the calculator. If you have yourself one of these calculators, you can solve. Show it again. You can solve simultaneous equations easily. Save time on the exam. So get x is equal to 1 by 15, 4 by 15, and yeah, sorry, that's y. X is equal to 1 by 15 and y is equal to 4 by 15. Okay. So the point common to both planes is going to be 1 by 15, 4 by 15, 0. Z is 0. Okay, so that's one part, half of the question complete. We just need to find the direction now of the line. So the direction is again going to be just the cross product of the two normals. You see, if we have two planes like this, and they intersect over here. See, this plane is going to have a normal and this plane is going to have a normal. And they're perpendicular. The cross product is going to be perpendicular to both. It'll actually have the same direction as the line of intersection. So that's why we want to take the cross product of the two normals. So let's take it. It's going to be I, J, K, 3, 3, 2, and 1 minus 4, 3. So it's going to be AD minus BC. So 3 into 3 minus 8. It's going to be 9 plus 8, 17. Okay. Yeah, 17. And then we have J, 3 into 3 minus 2 into 1. That's going to be 9 minus 2, that's 7. Sorry, and don't forget the minus when putting the J's, it's going to be a minus 7. So K, and for the last row, we got 3 into minus 4, minus 3. So that's minus 12 minus 3, that's minus 15. 15. Yeah, minus 15. Yeah. So that's our direction vector. So now we can just say that the L is going to be equal to 1 by 15, 4 by 15, 0, plus T into 17 minus 7 minus 15. Okay, so the curve C has polar equation. This is the next question. So the curve C has polar equation r is equal to e to the minus theta minus e to the minus pi by 2. Sketch C and state in exact form the status distance of a point on C from the pole. So for this, what you have to do is go to your the table function on your calculator, enter the function, and put various values of the theta until you get enough points to plot the graph. So that's a bit complicated, but I'll just draw the graph. It's not that difficult. I think so. You should be able to do it by yourself. Okay. Okay. Let me just draw it one more time straighter. It's going to be theta is equal to 0 and theta is equal to pi by 2. This is the origin. This is the pole, as they say. So the graph's going to look something like this. So see, when theta is equal to 0, you get e to the minus 0 minus e to the minus pi by 2. So e to the minus 0 is just 1 minus e to the minus pi by 2. So this is the point. 1 minus e to the minus pi by 2. So it goes, okay. So all the way like this. Until it finally goes down like that. So that's how the graph looks like. So the greatest distance of a point on C from the pole is nothing but it's obviously this one. So this is obviously the greatest distance. So it's the greatest distance is 1 minus e to the minus pi by 2. Find the exact value of the area of the region bounded by C and the initial line. So that's just find this area basically. So let's do that. So that's area of a polar graph is going to be half integral of alpha to beta r square d theta. Okay. So we can easily do that. So they gave the bounds of the curve from 0 to pi by 2. So let's do that. 0 to pi by 2. And they gave r as e to the minus theta minus so that's going to be squared d theta. That's going to be half integral from 0 to pi by 2 of e to the minus 2 theta square it. So expand the brackets, basically e to the minus 2 theta minus e to the minus plus e to the minus pi minus 2 e to the minus theta into e to the minus pi by 2. Okay, what's this going to be? This is going to be 2 e to the minus pi by 2, e to the minus theta minus pi by 2. Okay. So we can split this up into some bigger integrals, a smaller integral, so this becomes half times. Okay, or we can just directly do it, it's not that difficult. So e to the minus 2 theta by minus 2 plus e to the minus pi times theta, integral of a constant, this is a constant. This is going to be that times the variable. Minus 2 e to the minus theta minus pi by 2 divided by minus 1. So this is going to be plus. And we are evaluating this over the region 0 to pi by 2. So substitute the values of pi by 2 and 0, and then we get, what do we get? We get something like, so it's going to be half into minus e to the minus 2 times pi by 2 plus e to the minus pi times pi by 2 plus 2 e to the minus pi by 2 minus pi by 2. This is going to be minus pi. Okay, and that's going to be forget about that. Let's move on to the next one. Minus, substitute 0 into all of this, we get e to the minus 0 is going to be minus 1 by 2 plus 0 plus 2 e to the minus pi by 2. So simplifying all this, we get 1 by 2 times e to the minus pi by 2 1 by 2 times, what is this? 3 by 2 e to the minus pi plus pi e to the minus pi by 2 plus 1 by 2, right? Check. 3 by 4 e to the minus pi plus 1 by 4 pi e to the minus pi plus 1 by 2. Yeah, okay. So that's our answer. So write it neatly. It's going to be 3 by 4 e to the minus pi plus pi e to the minus pi by 4. Oh, I missed something. So minus e to the minus pi by 2. Yeah. Minus e to the minus 2e. Yeah. I can chop this one up, but hope you guys still understand. Yeah. Okay, so show that at the point of C furthest from the initial line, 1 minus e to the theta minus pi by 2 minus tan theta is equal to 0. Okay. So from the initial line means dy by d theta is equal to 0. That's the condition. So dy by d theta. So first let's find out what's y. So we have r is equal to e to the minus theta minus e to the minus pi by 2. So y is nothing but r sine theta. So r is equal to y by sine theta. So y, this is y by sine theta actually. So y by sine theta. And multiplying both sides by sine theta, we get y is equal to e to the minus theta minus e to the minus pi by 2 times sine theta. Right? So dy by d theta is just going to be, use the product rule. So you get e to the minus theta minus e to the minus pi by 2 cos theta plus minus e to the minus theta times sine theta. Okay, and this is going to be equal to 0. So let's solve this equation. Let's simplify it. So let's divide by cos theta first. So we get e to the minus theta minus e to the minus pi by 2 plus, okay, minus e to the minus theta tan theta is equal to 0. So this just becomes, yeah, we can just erase that minus and move everything a little to the left. Okay. And let's divide everything by e to the minus theta as well. So we get 1 minus e to the minus pi by 2 divided by e to the minus theta minus tan theta is equal to 0. So this just becomes 1 minus e to the theta minus pi by 2 minus tan theta is equal to 0. So it's shown That's the equation we have. We reached it. And verify that this equation has a root between 0.56 and 0.57. So to verify that equation has a root between two values, you have to just substitute these two values into the equation and show that there's a sign change. So for example, here when we substitute 0.56, what do we get? 1 minus e to the 0.56 minus pi by 2 minus tan of 0.56. Make sure you're in radians. So you got something like at theta is equal to 0.56, we have 0.00912, and at theta is equal to 0.57, what do we have? We have minus 0.0085. Okay, so since there's a sign change, since there is a sign change, you see the plus over here and minus, there is a root between 0.56 and 0.57. That's all. So this is the seventh question. The curve C has equation y is equal to f of x, where f of x is equal to x squared by x plus 1. Find the equations of the asymptotes of C. So the first one is obvious, it's the vertical asymptote at x is equal to minus 1, in which case the denominator is equal to 0, so there will be an asymptote there. There will also be a oblique asymptote, because we see the degree of the numerator is 1 greater than the degree of the denominator. So to find the oblique asymptote, we have to do long division. So x squared divided by x plus 1, it's going to be x, so just like 0x here. So x squared plus x. So dividing, subtracting, get minus x plus 0. So minus 1, we have minus x minus 1. We get 1 here. So we reach the remainder. So the oblique asymptote is always just going to be this thing. This is the quotient. So oblique asymptote is going to be y is equal to x minus 1. Okay. So yeah. Okay. So question B. Find the coordinates of any stationary points on C. So we know that stationary points happen when dy by dx is equal to 0. So y over here is x squared by x plus 1. So dy by dx is going to be equal to x plus 1 into 2x minus x squared into 1 divided by x plus 1 whole square. And this is all equal to 0, right? So cross multiplying, we get x plus 1 into 2x minus x squared is equal to 0. So 2x squared plus 2x minus x squared is equal to 0. So x squared is equal to minus 2x, right? So now we can just obviously tell x is equal to 0 is one solution. Dividing both sides by x, we get x is equal to minus 2. So that's another solution. So when x is equal to 0, so what is y? So y is also going to be equal to 0. And when x is equal to minus 2, we got minus 2 squared by minus 2 plus 1. So that's obviously 4 by minus 1. That's going to be minus 4. So those are our 2 points. We got 0, 0 and minus 2 comma minus 4. So these are the stationary points on C. So let's sketch C. So we got the xy axis like this. It's the y-axis. And this is the x-axis. So we got one vertical asymptote at x is equal to -1 here, and another one at x is equal to y is equal to x minus 1. So that's going to be something like this, right? And they gave us the information of two turning points. One is at this 0 comma 0, another one is at 0 minus 2 minus 4. So using that we can just complete the graph. It's going to be something like this and this. Okay, so that's I can draw it to make it fit a bit better. So just give me a second. So this is the graph. Okay, find the coordinates of any stationary points in the curve with the equation y is equal to 1 by f of x. So we have the regular y is equal to x squared by 1 plus x, regular f of x squared by x plus 1, yeah, same thing. So 1 by f of x is going to be 1 plus x by x squared, right? So let's find the dy by dx of this and set it equal to 0. So it's going to be x squared into derivative of 1 plus x is going to be 1 minus 1 plus x into 2x divided by x squared is equal to 0. So cross multiplying, we just get rid of the denominator and we are left with x squared minus 2x plus 2x squared is equal to 0. So x squared minus 2x squared is equal to 0. Minus 2x is equal to x squared. X is equal to 0 and x is equal to minus 2 again. So it's the same x coordinates as the previous one. So clearly x equals to 0, you can't actually, it's not an actual stationary point, because if we see, when if we substitute it over here, the denominator is going to be 0, so that can't be a valid solution. So it's only x is equal to minus 2. And when we put that, we have, in the calculator, we get y is equal to minus 1 by 4. So this is the only stationary point. It's going to be minus 2 minus 1 by 4. Okay. Okay. So this is the last part. Sketch the curve with the equation y is equal to 1 by f of x and find in exact form the set of values for which 1 by f of x is greater than f of x. Okay. Let's put this something like this. Now from this part, we had the graph over here, it's obvious that x is equal to 0 is going to be an asymptote, right? So there's going to be a vertical asymptote at x is equal to 0. And they gave one stationary point as minus 2 comma minus 1 by 4. So somewhere over here. Now, yeah. So if we take the limits as, see, if we check this function, or alternatively, what you can do is just graph a few points, and what you get to realize is that the further to the right or the left we go, the more closer it grows to 0. So this part is going to be looking something like this, and this part is going to be looking like this. So that's the graph of 1 by f of x. And let's find the values for which 1 by f of x is greater than f of x. So just like superimposing the graph of f of x over here, we have something like this. I'll draw it in a different color actually. right? And we had here at -2, -4, we had another turning point, something like this. So we're asking 1 by f of x is greater than f of x at which points? So now it's a bit obvious to us that clearly in this region it's going to be greater, and also see there's kind of there was an asymptote here at x is equal to -1. Also in this region onwards, right? So one answer is obvious, one region, it's going to be x is less than -1, right? And the other region is going to be, let's find out the coordinates of this part. So these are where the graphs intersect. So we have 1 plus x by x square is equal to x square by 1 plus x. So 1 plus x whole square is equal to x square whole square. Taking the root on both sides, we get x square. So x square minus x minus 1 is equal to 0. So solving this, we get 1 plus root 5 by 2 and 1 minus root 5 by 2. So x has to be between these two values for 1 by f of x to be greater. So 1 plus root 5 by 2 and 1 minus root 5 by 2. And that's it. These are the regions where 1 by f of x is going to be greater than. So we might also have to mention that x cannot be equal to 0, because at x is equal to 0, we have it's kind of tending towards infinity, right? Okay, I think so it's fine even if you don't put x is not equal to 0, but I think so it's better to put it as a safe option.
Alright, thank you everyone for watching the video, and don't forget to hit subscribe to stay tuned for more episodes coming in the way. Goodbye and see you in the next video.